Okay, so this is the guy here. And the fact that you get this grammar, this is in A is a starting symbol. Sometimes it's B, sometimes it's C or whatever. So A is the starting symbol. And then you have A goes to 1, 0, A, etc. And A goes to 0, B. So each one of these will produce transition in the machine. So what is this for? This is telling you what the grammar is. And as soon as you see starting state is A, you know, why am I not able to do these things clean? I think I will put it like that. No, that's good enough. Sure. Okay, so I can see everything here. Good. Yeah, and that's good enough. So I have G, and then I can see that. That's what I wanted. So this part here is that. So you get the initial state. And so it's just a mechanical process. So everybody should be able to get this. So because whatever the grammar is, you go here 1, 0, 8. So you go okay, 1, 0, 8, and that's it. If it was 1, 1, 0, 1, 1, 0, so you'll have 2 extra states, and then you'll go to here. So whatever it is, that part there is done, and that's this part here. Then A goes to 0, B, A, and you put a 0, and you get B, that part is done. So each time I tick a part, I will show you. And then B goes to 1, 0, C, so you put 1, 0, and C, so you have to put an intermediate state here. That's done. And then B goes to lambda. Now, what does that mean? It means that B is an accepting state. That's why it has a double circle. So that part there is done. C goes to D. C, you put the D with a lambda, right? And you put a lambda there, right? And then it means C can go instantly jumping without any input. And lambda is like no input, empty string. Then, unfortunately, I made a mistake here. I am getting old. So I'll fix it and then put it back. So D goes to 1E. So there's supposed to be a little arrow like this, and there's supposed to be a 1. So I lost a point. Because if you did that, that's how, I know you know what to do, but 1 point doesn't kill anybody. So I lost 1 point. Hopefully, I'll still get an E. So we did each one. So as you do them, you say, I did this, 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 I did this. Then E goes to 0, 1. So E goes to 0, 1. So that's the new state you created. And this is the E goes to 0, 1. So this is done. Then E goes to 0, C. It was 0, you put a C, this is done. And so that was done. And then finally, C goes to 1, 0, C goes to 1, 0, 1, and 0, that's done. And then that's it. I underline everybody. This was done, this was done, this was done. And then you make a look back and you think, is my machine okay? Now, I forgot one thing. I forgot F. F goes to 0, B, right? F goes to, after E goes to 0, C, I see F goes to 0, B. So you put F and you put 0, B. Now, some students are thinking, okay, professor, why did you put that? Well, I agree that it is not, accessible from A, but you just convert it mechanically. So this is an algorithm you're doing. Whatever you see here, you put there. And that's the correct way. Now, if you had not put it, I guess it says find an NFA which is equivalent to this RLG. So this NFA, if you include F or you don't include it, it is still going to be equivalent to the grammar Y, because the F is useless. The F is inaccessible. But I encourage you to put it because so that you went through everything, even though it's useless. Because we are not trying to minimize the machine or whatever. But if you want to go ahead, and the problem is if you try to minimize the machine, you might get it wrong. So nobody's asking you to minimize the machine, right? That's a different question when the partition algorithm. So you minimize there. Nobody's asking you to find, you just have to kind of mechanically convert. So I hope this is okay by everybody. So let me put a little tick here and said, that's this solution. And even though this is a you know, this is the part. You're thinking, we don't know what stupid things, you know, they are asking us to do here. It doesn't make sense because it's not numbers, it's not graphs, right? It's just ugly stuff. Well, that's why the course is ugly. And that's why it's called theory of algorithms. But if it, maybe you should call it, you know, theory of stupid things. But whatever stupid thing is, if you are signed up for the course, this is the thing you got to do. So I hope everybody can get that, because so that part is done. Then they say find an RLG that is equivalent to this machine. So you say, okay, the initial state is A, right? So that converts to that this is a starting symbol. So it's two different things. This was the starting symbol. Now you got this, and this is the starting symbol, right? So you're thinking, okay. And then in this machine here, so I did that. A goes to one thing, CB. So A goes to CB, I got that. That's done. So I got that there. B goes to DC. B goes to DC, right, like that. And B goes to BD. So B goes to DC, that's this. And B, where is the other B? B goes to BD. B goes to BD. So you got those two, right? Then how about C? C goes to BC, that's this arrow here. BC, B capital C. C goes to C capital D, that's this little C capital D. And C doesn't go to anything else. So there is no more C. Then D goes to DA, D goes to DA, so little d capital A, so that's this. D goes to AE, that's this. And then E goes to BA, E goes to BA, that's this. And finally, I say E goes to lambda Y, because E is an accepting state and nobody else is an accepting state. That's why you get this E goes to lambda, that's because of this. So this thing you can do in like 4 minutes or whatever, and or less, but you get that, and then you're thinking, okay, I'm done. Now, when I'm not telling you to do this at the beginning, but if you want, you could check that I got the total number of things, because you're thinking, okay, I got one initial, one accepting, so that should give you, you know, one initial, one accepting, and 8 transition. How do I know 8? 1, 2, 3, 4, 5, 6, 7, 8. And that's, you know, so you get 10 productions, 10 productions. And you're thinking, okay, I got my 10 productions, I'm good, right? And nothing more to it. Now, this one is a little harder problem. So part A says find a regular expression for which this thing here. So let's tick off all these tick marks, because they are just, you know, a pain in the rear end. So pain in the whatever. So tick off this. You know, I don't want to, because we did it. Okay, so what do we do? Well, we start with the original machine, and then we eliminate B. So you're thinking, who is B? That guy here. So if you eliminate B, it means, I gotta go back to this. It means you gotta take care of that root there, and take care of that root there. So you will get, yes, does it matter which state you eliminate first? No. So good question. It doesn't matter which state you eliminate first, but it makes sense to eliminate the easy state first. Because, okay, you could try to eliminate D. Okay, first of all, you cannot eliminate A and you cannot eliminate E. Those two are the beginning and ending, so you cannot eliminate those. But you can eliminate these 3. And if you try to eliminate D, it gets complicated. But you could, right? But you're going to think, how can I eliminate D? Okay. I will get to that after I finish the question, but I'll show you how it gets complicated. But if you eliminate B or you eliminate C, it's a lot easier than D, because D is the problem guy. So I show you this arrow going this way and this arrow going this way, because that's when you lose B, you lose those 2 roots. So I put C and D, that means you can go like this, that's the CD, that's this. And then I still have the loop here, And then I still have everything else here. And I still have the D goes to A and the D goes to E like that. And the E goes to capital A with B. But I got a CB here now. So this is C and a B to D, from A to D. So from A to D, you get a CB. So you're thinking, okay, you eliminated B and you got two things. How do I know how many things I will get? Well, you look at how many things are coming into B. 1. And how many things are going out? 2. So you should get 1 times 2, which is 2 new transition. And that's what happens. We got 2 new transition, and I put 2 tick mark against them. So let me make this tick mark nice. Now, again, if these were numbers and you will see the significance of these numbers, you'll think, I get it. But you're thinking, I don't get it. What are these stupid things we're doing here? Well, it's theory of algorithms. It's stupid. But, you know, you got to live with it. So you got these 2 things here. Then now you're going to eliminate C. So the D is here, the E is there, and so you're thinking, I'm going to eliminate C. So you're thinking, okay, if I eliminate C, I will just get, what about C? 1 thing comes in, right? And 1 thing comes out, and you have a loop. So forget the loop. You will only get 1 new transition. So this is C, and I'm putting in this, you know, to show you 1 is coming in and 1 is coming out. And then you have loop and so on, but that doesn't matter. I will tell you what the loop does. So you look at it and you say, if I cut out C, I'm going to lose CD and then all these B's here and then C. So that's why you put, you know, CD times B star times little c. And so that's what you go from A to D. And nobody else goes through C because you only get 1 new thing. And then you're going to say, oh, where did you get that CB from? Well, that CB is this. So I put plus because this is like 2 arrows. 1 arrow like this and then 1 arrow like go around there. And you're thinking, oh, okay, I see. You're trying to make the diagram simpler. Yes. Then finally, you get to eliminate D. So you're thinking, oh, just 1 thing is coming in and nothing is coming out. So you're right. So it will be this times the whatever that is, E, right? So CB plus CD, B star C, and then where did I get D from there? I don't know. I guess you're going to get, okay, you're going to get 2 things. I apologize. You get a D going there and you get an A going there. So when you're eliminating this D, right, that is my fault. There is a D here, right? That's that D there, right? Because I was thinking, where did the D came from? And it has a little underline. But you can see it there. It's just that I didn't put it. But that is bad. So but I know what I was doing. So I said, okay, you are going to get 1 like this and then 1 like a loop. So the loop 1 is this. So it's CB plus CDB star C and then times D, that is from A to itself, and then from A going through to E. And so it is CB plus CDB star C times A, which goes from here to here. And then that's it. There's nothing more. And then you're thinking, okay, now you are ready, because when you're down to 2 states, you're ready to get the final answer, right? And so when you're down to 2 states, I apologize for this kind of, you know, messy diagram or whatever, but, you know, what happened is, I am not sure, but I guess in this fall, I had to hurry and do their test quickly, and I kind of forgot that, so I apologize. But, you know, I hope the person grading me wouldn't kill me, because I did get the right answer in the end. But I deserve some credit, you know, because I didn't put it. So CB plus this is a loop here, right? And then this B is that, right? And then going this way, it's that and that. And then there is no loop here, because there is nothing from E to E. So you got your R1. So according to the thing you memorized, the L of M is R1 star. So what is R1? R1 is the loop here. What is R2? R2 is what comes across. So that's R1, that's R2. What is R3? R3 is what comes from here to here. And R4 is the loop at here. But there is no loop there, right? So you're thinking, okay, the R4 is empty. Okay, and so everybody's like, but that's tricky. Well, yes, but you know, sooner or later you got to put some question that tells you what is R4. So you got to, you know. So it's good that you guys are seeing it. But in the class, when they were asking, Professor, there is no loop at E. I said, well, if there is no loop, put what no loop means. You know, you are not always guaranteed to get a loop, right? And so put what no loop means, which is empty set, right? There is nothing going from E to E. And then according to the formula for L of M, you get R1 star R2, and then you get R4 plus all of this, right? Star. So R4 times R3, which is this, times this star, and then R2. And so you're thinking, oh, okay. And then you just plug it in, and then you get your final answer, right? Now, you can see that question number 2 is reasonably short again. And then they ask, write down what the halting problem asks. But before I go further, is this okay by everybody? Because as I said, whenever the professor, like I can show you another test, and let me show you the other test, right? Because I mean, I have another test here, spring. Now this test is nicer because it's cleaner and come on. You see how I got to draw a straight line diagram, I got to photocopy, etc. And here, it's almost the same as this guy here, you know, but it's slightly different. I had B as the starting symbol. And then here I had C as the starting state. So this becomes the starting symbol when you go to the RLG. And that's shown here. So B is the starting symbol, and then C was the starting symbol here. Right? So you think, oh, okay, same problem. And then everything went out nice here, and I give a slightly definition, but the point of it is this was done better because, right, I had the time plus, right, I got the university photocopying machine, but now I got to do everything by hand on the computer. I got to grade you by computer. I got to do everything by hand because my printing doesn't work on the university from home, right? And then whose computer I have the university's computer, so my computer is no good, it's not compatible with their system, so I can't do all the things they want. And even right now, there's some problems, but I am working within the system. So I have to make your test, and last semester this happened, I have to make your test a little bit ugly like that, and for that I apologize. But this is hand-drawn using a mouse. So go back to the 2020 test. And Santa Maria. This here, plus. Okay, good. Let's look at the second question. So the first question is done, the second question is done. And it says, write down what the halting problem asks. This is 2B. What does halting problem ask? Halting problem is, you're basically asking when does a Turing machine halt, right? On a given input. So it says, is there a Turing machine H such that for an arbitrary Turing machine M and an arbitrary omega, H will halt on this in an accepting state if M halts on W, and H will halt on C of omega in a non-accepting state if M doesn't halt on omega. Right, so let me underline all of that. Now, some people will say, wait. What is the point of that C of M? Here C codes the Turing machine M, and it's input into the language of H. Every Turing machine comes with a certain language, right? So like every computer has an operating system, and if your operating system is Unix, or your operating system is Windows, or your operating system is what Apple's one is, I forgot what Apple's operating system is, but whatever it is, whatever your operating system, it has its own alphabet, etc. Before you put anything, you got to code it in that person's language. So the Turing machine M could be any crazy machine with its own alphabet, and it has its own input alphabet also, because the input alphabet is always a subset of the tape alphabet. So all you're saying is, hey, put it in the alphabet of the Turing machine H, and then H is supposed to decide whether M will halt on omega. And it says, is there such a Turing machine? So that's what the halting problem asks. And the answer is no. That's because the halting problem is not decidable. So there's no Turing machine that says yes and no in a finite amount of time. So you're thinking, okay, I understand. So what are you supposed to write? Whatever I wrote here, right? And so that is the purpose of the C of M and this sharp C of omega, because you put the code of the machine, then you put the omega. Okay, so far so good. Now, we go to the next question. So the first two questions were all from chapter 4, and then the last question is also from chapter 4. So there are 3 questions from chapter 4. And sorry, the 2B was from chapter 5. So there's 1.5 question from chapter 5, and number 5 is from chapter 5, which is Turing Machine. And there are 2 questions from chapter 6. So I kind of roughly spread it out evenly, but chapter 5 is not as important as the chapter 4 and chapter 6, because we do things just on the surface, because we don't, I don't assign you, find a Turing machine. I just say, tell me what this Turing machine does, and why is that so? Because Turing machine is a very complicated thing, right? And so it's hard to find Turing machines, but it's not impossible. So when you do graduate classes, you have to do that. You have to find Turing machines. So in Theory of Computation 1 at FIU. So third question is, define what are the initial functions and what is this operation called primitive recursion. So this is a question that confuses many people. They know what are the initial functions, but they don't know what is the operation called primitive recursion. So there's 2 things. There is the operation called primitive recursion, and that's why I wrote define what is the operation. And this is not good. So define the operation, and there is something called primitive recursive function. That. So you're thinking, there is a difference between the 2? Yes. But they look almost same thing. You see the word primitive recursion, and when you see primitive recursive. So one is an adjective describing a function, one is a sort of like a noun, primitive recursion. So the initial functions are the constant 0, the 0 function of one variable, c of x, the successor function, and the projective functions I n sub k of x1 to xk, which is equal to xk. And you're thinking, oh, okay, I agree with that. Then primitive recursion is that operation that takes a function g, maps n to the n onto n, and a function h maps n to the n plus 2. So it takes a function of n variables and a function of n2 plus 2 variables and produces a function f of n plus 1 variables. And you see the recursion is done on the last variable, which is the n plus first variable, which is the y. And it is defined like this: f of 0, x and 0. So now you can see that on the line clearly, f of x and 0 is equal to g of x. So there is a line here. I hope you see it, but let me just brighten it and brighten this line here so you can see it's a vector. X is equal to x1 to xn, right? And f of x comma s of y, again, it's a function of n plus 2 variable because there is n variables here. There is 1 here and there's 1 here. So it's n plus 1 more, right? So that's why it's n plus 2 variables, right? And it says, okay, you have this definition, f of 0 is this, f of s of y is this. And then that's your definition, right? So you think, okay, so I am not confused. Primitive recursion is an operation that produces from 2 functions, g and h, a function f, correct. And then what is the primitive recursion? Primitive recursion is, a function is primitive recursive if you can get it from the initial functions using primitive recursion, composition, and Cartesian product. So you think, okay, I got that. I read it. I saw it. But, I didn't like it. Okay, that's the problem. Nothing here is, likable. So you want to get a program for this guy here. F of xy is equal to 3x plus 5y. So you're thinking, I don't know how to do this. But if you look at the previous test, you will see there are many things like this. Joshua wrote, it is best to eliminate the vertices with less edges coming out and going in. Correct. You know, so Jose Caro Muna took out 2 points. Thank you, Jose. You're very kind. I'll do the same to you too. Be kind. So here is the question. Where do you start for 3B, right? So you just say, well, let me see what he did in that previous exam, right? And in the previous exam, I said, I will show you just like I said here, right? In this one here, he said, f of xy is this, right? So I showed what f of x0 is and what f of x successor y is. So f of x and 0 is equal to 3x plus 1. So you're thinking, yeah, you're right. But where are you going here? So because the y is 0, that's 3x plus 1. But where are you going here? I said, wait. And then f of x comma s of y is 3x plus 5y plus 1. So you're thinking, plus 1. So you're thinking, wait, how did you get that? Okay, the 3x is the 3x. The 5 is s of y is y plus 1. So that's 5y plus 1 plus 1. Because the thing says 3x plus 5y plus 1, but this is y plus 1. So let me just write y plus 1 here. So you can see what a successor of y means. Okay, and somebody will say, why didn't you put y plus 1? Well, you're supposed to put successor of y because nothing's supposed to really put plus, right? And I will again tell you, I'm not going to use plus, but you will see. So you're thinking, okay, I see what you say. So then I write it as 3x plus 5y, right? Plus 1 plus 5. So you're thinking, why did you write this? Because this is, f of xy. So you're thinking it's equal to f of xy plus 5. You're thinking, okay. So now you know what is the age of xy, f of xy is that. And the g is that. So you can see why the first person said g of x is equal to 3x plus 1, and h of x comma y comma f of xy is equal to f of xy plus 5. So you're thinking, how can I get h expressed nicely in terms of its input? Same thing for g, because I want to express f and g as primitive recursive functions, meaning in terms of the original things. So then you realize, wait. This is why, so the h and the g must be simple, right? So the h is just saying, you just took the last guy and you added 5 to it. So this is what this is doing. The last guy is the third guy. You have 3 input here, this, and this. This is x1 to xn, this is y, and then this is f of xy. So you're thinking, and all of these x's have an underline under them, right? So remember that there's an underline under them because this represents x1 to xn. Right, but it doesn't show up because of the poor quality of the scanning. I tried to scan the best I could. Now, I put h is equal to 1, 2, 3, 4, 5 successor of this. So it's basically you take the f of xy and you add 1 5 times. You're thinking, and you say, why did you write it like that? Because I want to show h can be obtained from the initial functions using composition and the, whatever you have, and Cartesian product. And then the problem with g is 3x plus 1, and 3x plus 1 is not an initial function. So you say, well, I will make it an initial function. No, you can't do that. You just write it in terms of the initial function. Or you put, g of 0 is equal to 3 into 0 plus 1, because g of x is equal to 3x. Where is that here? Plus 1. So it's 3 of 0 plus 1, which is 1. So you're thinking, okay, I got that. G of 0 is 1. And g of successor of y is 3 times the whatever you get here, 3 times the y plus 1, because that's successor of y plus 1, which is 3y plus 1, right? 3 times y plus 1 plus this 3 times 1 plus 3 here, which is equal to, whatever that is. So now you want to say what g is. G is a function that is defined recursively. And you're saying, wait. I was trying to show that f is defined recursively. Why are you getting with g? Well, g was obtained from 2 functions. It was obtained from the 1, and then it obtained from this tree successor guy. So G is obtained by primitive recursion on successor of 0, which is this one, and tree successor here, which is this, the tree successor guy. And then you say, therefore, F is equal to the function obtained from primitive recursion on G on H. And so now it all fits together. And then you plug in the program for G, which is this whole thing here. From here to here, you plug it in all here. And then H, you just plug in H, whatever H we got here. Now you're thinking, what is H? Well, H is here. H is 5 successor of the last output. You're thinking, oh, okay. So you're done. And you have a full program. F is equal to PREC, and this is a program, this is another program, and everything works out. Now, you got to ask yourself, and this is again, I am hesitant to do this because every time I change things, but every test that you had, for the last, whatever, like let's look at the next previous test, fall 19 or whatever. You're saying, I just think same thing, 2x plus 3y, let's go again. Spring 18, 2x plus 3y plus 1, I guess I saw that already. Then spring 217, 2x plus 4y plus 3, what was this? 2x plus 5y plus 1. I mean, God knows what you can put. Anything you can put that is reasonable. And always, like here, number 3, we got a nice thing. We got the H is this, and then you got F is equal to primitive recursion of this is the input, this is the output, right? And you got whatever. So the way to understand this problem 3 is to look back and see how many different times it came and how you find the G, how you find the H, and then how you say F is equal to primitive recursive function coming from G and H. And it's designed like that. So much for that. My eyes are bothering me. Let me see if I can have a drink or something, but I don't know if that will help. So that takes care of 3B. Now, number 4. They're asking in number 4, so I got to go back and give you the question. In number 4, they're asking, they said, hey, senor, I hate this thing,
Excuse me, Professor. For 3B, when you're finding G, what is the thing next to the S sub O in G for the first parameter?
Here?
Right under that. Yeah, that right next to the SO.
Okay. There is no S. G is G of 0. Oh, here, you mean?
Yes.
Okay. That's an underline. Let me take out the underline. So G of 0 is 1. Now, G is a function. So I'm trying to write, G is a function obtained from primitive recursion. So PREC of G1 and H1. Because G and H are, F is the function like this. F is this. So we already use G and H. But G was 3x plus 1, and 3x plus 1 was not an initial function. So this, how many variables this is? 1 variable. How many variables does this have to be? 0 variable. And how many variables does this have to be? 2. Because this is always, H1. I got to put H1 here, and I got to put a comma here. So your question was, so I ended up getting this G1 was this. So G of 0 is equal to this. So so the G1 is just this one here, and that's this. So that's my G1, if you like. And this is my H1 here. Because G is primitive recursive function obtained from G1 and G2, and this has to be 2 variables. So what about the H? The H is G of successor Y is 3y plus 1 plus 3, which is, G of Y. So this is G of Y plus 3. So it is remember, this one was h of xy and f of xy. The h1 will be h1 of y comma g of y, because it's a function of two variables. So what happens is that you get a nested level, right? You get a nested level of, this didn't come out nice. You get a nested level, and take this out. Okay. H1, when H1 was this, it was, you're defining f as the function obtained from primitive recursive function on g and h. G was one variable, h was three variables. What were the three variables? X, y, and this, the f of xy. This h1 is a function of two variables, y, and there's no x, and g of y, because g of y is just 3y plus 1. So you're thinking, okay, g of s successor y is 3y plus 1. So I got to express this in terms of that. And so then it's g of y plus 3, so that's why it's successor of I22. Successor of the second thing. This is the second thing. And that's how you get this, and this is how you get s of 0. And you're thinking, okay, your s of 0 is obtained by plugging in g of 0. Your this part is obtained by plugging in s of y here, right? To get, express g of this in terms of the original g. And so it's this plus 3, and that's why there are 3 successors. And so therefore this is so. And the reason I was writing this short is because every year I did it. When I did it with this function, and the previous year I did it, every year I did the same thing. So I said, there is no point in putting all the details every time and, bore you to death. Just show you how I got the 1, and show you how I got a 3, and so I should get 3 of whatever this is. 3 of s of, the y, because this is g of the y. So g of s of y is equal to g of y plus 3, right? And that's why this is 3 successor here. And then now I write g is this whole function here, and h is this whole function here, successor of this, because h is how many successors? 5. 1, 2, 3, 4, 5. And I put that's the h here, and this is the g. And then I'm done. Now, I am, because you asked the question, and I hope I wouldn't bore everybody, but let me go back here and show you what happened. I am not going to go through the whole full details, but let me go back and show you what happened when we did the same question, and it was a different thing. So I said same thing, initial functions and whatever, and move it a little bit here. And we will find primitive recursive function g and h such that f is equal to primitive recursive function on g and h. Then I found f of x and 0, I got the g, I got the h. Then I said h is clear cut. H is the 4 successors. And then the g, okay, also we will express g as prec g1, h1. So you're saying, oh, you were giving more details here than then. Yes, because I didn't want to bore you to death here. But you could write all this. And then you say g1 maps g n0 to n, h1 map n2 to n, and then the g of x is 2x plus 3, so g of y is 2y plus 3. So you're thinking, why do you write it in terms of y? Because we are trying to define g in terms of g1 and h1. So g of 0 is 3, and g of s of y is g of y plus 1, which is 2y plus 3. 2y plus 1 plus 3. So it means that you get g of y, s of y is g of y plus 2. Because remember what g of y is. G of y is 2x plus 3. So this is the 2y plus 3. And then the plus 2 that's this. And so then g of 1 is 3. So you write g of 1 as successor is 0. And you write h of 1 is successor of I22. So in the end, this will be your, if I can draw here, come on. I don't know why this thing is not helping me. It's bulking. Read aloud. Okay, it refuses, something is wrong with the computer, because you can see on my screen there is, Okay, I gotta go back here. I don't know what it was doing here. But you can see that the G was 3 successors of 0. This is initial. And the H was 2 successors of I22 because the H was, this is H1. This is not this because the G was 2x plus 1. So you can see from this, you're starting out the 3 and each time you're adding 2 more. So that's what the H1 is, adding 2 more. And the G is what you start out with, right? But you can't write all of that. G is what you start out with, the G1, and H1 is what you add each time, at each step, because then that's too babyish. But then you see G is going to be the function obtained by primitive recursion on G1, right? This, and H1, and then this is your G1, which is that, successor of 0. And then the H1 is this, so you put it like that. And then you say, okay, now I see what the G is. So this is the whole G, and this is the whole H. So the whole question boils down to, it's a double 2 layers. You could not get F quickly in terms of G and H. The H was good, but the G was complicated, and the G had its own G1, right? And its own H1, because the G itself was complicated. And so this one shows clearly how I did it. And then I did it there. I said, give you a game here, right? And don't do waste time, right? Because the more details you put, sometimes the more you confuse students. But sometimes you put less detail. So I have some details here. I have some more details, some less details here. But I am never sure how much detail to put, because some two students, if it gets to half a page, they give up. And then some students like, okay, I got this. But it depends on the student. So that's why I have both solutions. And I don't do the identical thing each time, because there's no point in doing identical thing each time. But you can see the only thing that changed is instead of 2x plus 3, this was 3x plus 1, right? So it means you start with 1 and each time you add 3. And that's what this is saying. Start with 1 and each time add 3. So you could have written that. Start with 1 and each time add 3. That's the recursion. But this is the way to write it. Now, I hope that answers the young man question who asked. Right? And I am sorry to take so much time, but this is important because this is a new topic. And the other things are like mechanical. Number 1 and number 2 were mechanical, but number 3 is not mechanical. Right? You got to think. Thank you, Jose. And okay. So now we are going to go into a similar thing, but this time we will have an easier time. So what is the question? Leave. Come on. I want 2 pages. And then this guy is not cooperating. Okay, so you. Okay, see, I put the thing at the end and it's not doing. But, okay, now it's doing, and then, okay, I gotta move it back. Okay, I want to show the question and I also want to show the solution. So now the next guy is same question, but what is the difference here? It says, what is the difference between partial and mu recursive functions on it? So partial function is any function that is allowed to be undefined at certain points. And that's what I put. A partial function is allowed to be undefined for some values of it. And the keyword is allowed. It doesn't have to be. It could be total. And then a mu recursive function is a partial function that can be obtained from the initial functions using this operation of Cartesian product composition, primitive recursion, and minimization on total functions. So you're thinking, that's a mouthful, but that's the definition. And so basically when you are asked, what's the difference? Write down the definition of the 2 things and then put in another sentence. That's what I did. So the difference is that a mu recursive function is a more restrictive kind of partial function. So basically, mu recursion says you can only get it in a certain way using these limited things. And partial function is you can do anything you want. You can define it whatever way you want, and it can be even undefined at certain points. And you're thinking, okay, so the difference is one is more restricted than the other. But how do you get the full credit? As long as you basically write what the 2 definitions are, you got the full credit. But this is like the icing on the cake to tell you, okay, that's the difference. And that they say, that tells you that you understand that there is a difference between the 2. But if you don't write the sentence, they say you don't understand. So the difference is that mu recursive is you obtain it from the initial function using a limited number of operations. Whereas partial functions, you can define it wherever you want, using anything, no restriction. And you're thinking, okay, both of them produce partial function, but one is a more restrictive kind. And that's the end of the story, mu recursive. And I would like to just say, define what is a mu recursive function. But they told me in 2019, ask a question like that, and it is not going down well. But I am in trouble. So I don't know. So that part is okay. As I said, write only your definition that you know of the two things and you're good, right? You'll get most of the points. You might lose at most 1 point for that sentence. Okay, so what is the other part of the question? The other part it says, f of x is equal to ceiling function of x squared plus 2 to the 1/3. Show that f is mu recursive function. So you're thinking, so then I added, you may use all of these, spread, monos, add, mult, and sign, are primitive recursive if needed, but you're not allowed to do so in question 3. Because in question 3, you could have done that and then everything would be too easy, you know? So in question 3, you have to do everything from completely scratch. So basically in question 3, your program cannot contain any higher level, functions. It has to be everything primitive. And here you can contain mult and monos and whatever. That's the whole idea. So you're thinking, okay, I got what you say. So the idea is, this is very short. Let g of xy is equal to x squared plus 2 minus y cubed. So you're thinking, where did you get that? And remember I told you, you just put this, right, is equal to y, or and then you cube both sides, you get x squared plus 2, and then you put minus y, and then you want that to be 0. Monos, not minus. And then you're like, I see. If this was to the 1/2, you would have x squared plus 2 minus y squared. So you say, okay, I know how to get the g, right? And then you say f of x is equal to smallest y, so the g of xy is equal to 0. So you say, okay, I got that. Now, what is more to be done? Well, the g, this, has to be written as the program. So you say f is equal to mu, so I guess I don't know where this 3 mark came from. There's like a 1 here or whatever, but there is no 1 there. That's just f, right? Because there is no f1 or whatever. And so f is equal to mu g comma 0, and then you say what is mu? Okay, mu is mu. What is 0? 0 is 0, so that's there. So 0 is 0, and then the mu is the mu, so you didn't do anything there. And then you have the square bracket, you square bracket. So what is the g? G is this guy here. And then you write that as best as you could in terms. Now, this is why I can write it in one line. Why? Because I have powerful things at my disposal. So you're thinking, what powerful things do you have? Well, g is a function of 2 variables, x and y. So you say, okay, I want x squared plus 2, so I pick out the x, so that's basically x, right? This is basically x, right? Because you got to pick it out from the 2, the input of g is x and y. Then multiply them, that's you get x squared. Then you take 2 successor, you get x squared plus 2. So you're thinking, oh yeah, x squared successor of x squared is x squared plus 1. Another x successor is x squared plus 2. Then you say, okay. And then you do the monos thing, so you say this monos the y cube. How do you get y cube? Multiply y by y, right? So you have to put this mult composed with I22. What is this I22 all about? It's picking out that y. So you're like, y multiplied by y. And then you say, okay. And then you get y squared. And then you say, multiply y by y squared. So this is another y. Multiply y by y squared, and you get y cubed. And you're thinking, oh, yeah. And you say, well, Professor, why can't we just put y cubed? Well, you are not allowed to put y or x or whatever. You have to put a program. So a program cannot have x and y. It has to be like monos, small circle, and this is a primitive program. It has to only have initial functions. This is a more sophisticated high-level program, modular program. It can have mult and monos and add. But, well, we didn't use add. But you were given permission to use spread and monos and add and sign. So I give you a lot of leeway. And so you can't just put, because if you put that, then you basically you're saying, okay, that guy G, this is mu G comma 0, and G is primitive, G is recursive. How do you know G is recursive? This proves that G is recursive, even though it's one line. And so after a time, you get the used to it, and you're like, okay, I pick out the x, and I have to have 2 more than the x, then I want the y cube, and so I hope everybody sees that. And it's not beyond your ability. Look at the definition is longer than the solution for part number 4, right? That's because we have high-level programming here, pred, monos, etc., and the thing becomes easy. So I hope you understand that the whole purpose of this thing is to write g of xy as a primitive recursive function, and then you put f is equal to mu g comma 0, and then you're thinking, okay, I'm done. This is the whole program, and this f, this whole mu, and all of this crap is the whole program for a primitive for a mu recursive function. It is not primitive recursive because it has this mu, but this is primitive recursive, right? Because I got it in terms of, and if somebody were to ask you, well, how do you know this guy here, x squared plus 2 monas y cube is primitive recursive? Then you could just take the whole program for monas, chuck it in here, whole program for mul, chuck it in here, whole program for mer, chuck it in here, chuck it in here, and everything becomes primitive recursive. But I am not wasting time to do that. That's why I said you may use this. So I hope everybody understands that. So you're like, okay, that bring it just like that. That's so short. That's 3 lines, right? Yes, it is 3 lines, but you got to know what you're doing, and that's why I keep saying do 5 exams. Why? Because if you don't know what you're doing, you're dead, right? All right. So, and you got many exams, and all of them is slightly different from each other, but all of them end up looking like this. And so, as soon as you do 5, you should be good. All right. Now let's move to the next question. It says, define what is Turing computable partial function. So you're thinking, I don't know what this means. No, it just means it's Turing computable and it's a partial function. You're thinking, okay. A partial function, f maps n onto n is Turing computable if what? If you can find a Turing machine that computes it. Now, if you write that, that's not right. Because we are trying to ask, do you know what compute means? So, if we can find a Turing machine M such that M halts in an accepting state with output f of n, if and only if n is member of the domain. So if you're in a domain, you have to halt and you have to have this input. If you're not in a domain, you do whatever you want. But I want you to halt and produce the correct output if I give you the correct input. That's what Turing computable means. You're thinking, okay, so we have to memorize these stupid things. Yes, because that's what you do in computer science. You memorize coding, memorize what each type of coding, each thing does, while and do, and, you have all of these specification of, things. So number 5, the definition is just that. Then there's the part B that says, what does this crazy Turing machine do? So the first question it asks in part B, it looks long, but it's very straightforward. It's like, what does it do in 1? You're thinking, okay, you mean I got to run through this machine with 1? Yes, because we are trying to see, do you understand what is Turing machine and do you understand how it moves? You're thinking, okay, but I hate the question. But if you don't practice, you won't get it, right? So you set it up and you say, okay, 1 is my input. So you have A and you have 1, right? And then you say, okay, 1 is my input. So A sees A1, what does it do? It puts an X and it moves right. That's the R is for right. And then it still stays at A. So you're thinking, okay, I agree. Then A sees a blank, what does it do? It replaces the blank by blank and it moves left. So it goes back under that X. And you're not seeing here, but in a good thing you will see it. I did underline it. But you're not seeing it because, unfortunately, the underline coincide with this line here. So B sees the X, what does it do? It says, oh, X, I'm going to replace you by 1 because, and I'm going to move right and I'm going to go to C. So it goes to C and it moves right and it goes under a blank. So now C is under a blank. So let me push this a little bit more this way. So C sees the blank. And C says, okay, I have 2 options. I can see a 1 or I see a blank. So C sees the blank and it says, I will go back to B and I will replace that blank by a 1. So it goes back to B and it moves to the left. That's what this L is for. So basically, this is just trying to tell you, do you understand how a Turing machine works? So it sees a blank, it puts the blank, replace the blank by a 1, right? And then it moves left, right? So it was there, it put a 1 there, and it moves left, it goes under that one, so under this one here. So let me put a dot over this one and dot over this one to show you where it went. Okay, and you're thinking, okay, after that, what does it do? Then it is at B, and B is seeing a blank. So B is seeing a 1, so B sees a 1, and it says move, replace the 1 by the 1 and move left. So it didn't move right, it moved left this time. So it went under this blank that is before these two ones. So remember, there is a blank before this one and there is a blank after this one, but it went to the left. Okay, so it went under that blank. Then when B sees that blank now, it says, oh, I am going to go to D and replace that blank by a 1. So this is the blank, right? So let me put a dot under this one. So that's this one, right? B sees, but you're not allowed to put dots because you're supposed to see, but it's to help you out. B sees the blank, it replaces the blank by a 1 and it moves one step left. And you're thinking, okay, I see when you put that dot, it helps me see where I move. I move 1 to the left of the blank and I replace the blank by a 1. Okay, and then you stayed in D. Sorry, you went from B to D. Then D sees the what? D sees the blank. And D sees the blank, it replaces the blank by 1, right? And it moves to the left and it goes to E, right? It replaces the 1 by blank and it moves to E. Then E sees a blank and E says, okay, I'm going to replace the blank by the blank and I'm going to move to the right, and it stops. So what it means now, the answer is 4, right? Because you have 4 ones and we are working in unary addition, unary number system. So you halt at F and it's an accepting state and you halt. So it means for 1, you get 4. And now when you do for 2, you will get 6. And for 1, you got 4. And then you can just check for lambda, you got 2. So you can guess now, wait, this guy, if I start with 2, each time I'm going to get 2 more added, I'm going to get 2n plus 2. So it could be 2n plus 3 or 2n plus 1, but in this case it's 2n plus 2 because the f of 0 is 2. And if you notice, when you go with 1, it replaces by 2. Now, if you understand it, Turing machine, this loop is the thing that keeps giving you 2 more, right? So you're thinking, oh, so you can see higher level programming or whatever. But the bottom line is, you follow your nose, and that's what we started doing. In the old days, we did something differently. So if you look at the old test, we were talking about language acceptors, etc. But now, they want you to understand what is a Turing machine and how it functions. So we are giving you these questions to say, can you follow it step by step with 1 and 1, 1, or with 1 and lambda? And then tell me what do you think it will do in general. And then you can make an intelligent guess, right? So this is not worth a lot because you're not proving. You're just saying, tell me, what function does it compute in base 1 notation? And as I said, this loop is the secret to tell you, give you 2 in the loop, and then when you come out, you get 2 more, and that's why you get 2n plus 2. You're thinking, okay, I think I buy that, but I don't like it. Well, that's why you do more questions to understand, because every test has one of these. And the recent test has it for Turing machines that are computing something in unary base. And that's why I said 2 examples. Now, the last question, I wanted to get to this, and this is the hardest, but at the same time, not a terribly bad question, right? But because it's a proof, many people get scared of it. So we are going to prove it here. So it says, determine which of the following languages are regular and which are not. So this thing says, the number of A's and B's, first you have to have all the A's and all the B's, and then the number of A's must be related to B like this. The K mod 3, the number of A's modulo 3 is strictly less than the number of B's modulo 3. So you're thinking, what does that mean? Well, you do the modulo of both, and then, so if you get 1 here, this has to be 2. That's the only possibility, because in mod 3, it's 0, 1, 2. If this is 2, then there is no possibility for this, right? Because you cannot be less. So you're thinking, okay, it means this can never be 2. Because if this was 2, how could this be bigger than 2? The 3 values of mod 3 are 0, 1, and 2. So you're thinking, okay, I got you. So what you do is, you say, look at n, because this is the thing you're going to compute. And you say, I'm going to look if n is congruent to mod 0 mod 3. That means you have, 3 times, an integer number of n's, of b's. Then k must be less than 2 into 0 minus 1, because this guy here is, n is congruent to 0 mod 3. So 2 times 0 squared, which is 0, minus 1, which is 2. So k must be equal to 0 or 1. So you're thinking, oh, so if k is equal to 0, if n is equal to 0, this guy here is 2 times 0 minus 1. This guy here is, where is this thing here? This guy here is 2. Right? The 2 doesn't come out good. Sorry about that. And their ink is also bad. So I will put, 2 here. So this could be 0 or 1. And then you're like, okay, 0 or 1 is less than 2. And then you say, okay. So what does that mean? It means that these are the 2 values possible for k. Then if n is equal to 1, then k mod 3 is less than 2, 1 squared minus 1, which is 1. It means the only possible value of k is 0. Right? So you're thinking, okay, what do you mean by that? Well, again, if this is 1, the only possibility for that guy is 0. And then if this is 0, right? I mean, you cannot, there is nothing that will be less than 0. So no possibility here. And that's why I put, if n is 2, then 2 times 2 squared minus 1 is 1. This is 0. So this did not occur. We just got another 0 for k, and this is the value of n. And you're thinking, oh, so these are the possible values. Yes. And so it says now you can get a regular expression. When n is 2, right? So n is 2. Where is that? N is, n is 0. Then you have 2 possibilities, 0 or 1. So you put 0 or 1 times, a multiple of 3, and then this is 0 for the n, because n is number of b's. When the number of b's is 1, modulo, so 3 times a, some integer plus 1, the number of a's has to be 0. And when the number of b's is 3 times, something plus 2, the number of a's is, 0, modulo 3. So it's a, and not lambda a plus a, or a times a star. And then that's your regular expression, you're done. You're thinking, that easy, yes, that's worth 6 points. And the other part is worth, usually 12 or 14, depending if the question is 20 points. So the last question is, you got this L2. And this thing was saying, if you say the language is regular, then you must find a regular expression for it. If you say it's non-regular, you must give a proof for it. So the last question is a proof, which is, out of all the things, just 14 points, and not 14, 12 points out of the whole exam. So you can get, without doing proofs, you can get, 88. And if you write some nonsense, you might get another 290, right? So you're thinking, okay, what is this saying? This is saying that the number of b's must be 2n squared plus 1, where n is the number of c's, must be greater than that. So it could be 2n squared plus 2 or 2n squared plus more 2, because it's an integer. It can't be 2n squared plus half. So you can suspect that this guy will be non-regular, and then you say, okay, look, I will prove it's non-regular because I'm going to do this thing here. I'm going to say, suppose L2 was regular. Then we can find a lambda free in Fe which n states such that L of M2 is equal to L2. Now, consider the string b to the n squared plus 2 times c to the n, right? So why did I pick that string? Because that string is the first thing that you can put here for b, because the k is equal to 2 times n squared plus 1, and it's the first thing that beats it. So that's why I put the k equal 2 times n squared plus 2. So that's how I got that 2n squared plus 2. It's the first thing that, the first k that beats this. You have to beat it. And the n was, the number of states in the machine, right? So you're thinking, okay, you pick capital N as opposed to little n, because n is a fixed number. And now what do? Then you say, now this string, because it satisfies the condition, it will be accepted. And then you're going to get a contradiction. And you say, since you get accepted and it has n plus 1 process the c to the n, you'll get a loop here. And if you write this loop twice, you will see that b to the n squared plus 2, that's the first part, right? Plus, right? Where is this guy? C to the I, 2 to the j, c to the n minus I minus j. That's the rest, right? So you're going through this loop twice. You go like that, and then you go like that. You only went through it once. So this part is this, 2 to the n squared plus 2. This is the c to the I, because the loop is between here and here. And you do this loop twice. So you will get c to the I, c to the 2j, this is 2j, plus n minus I minus j, because this is the balance. And these three are supposed to add up to n. And then when you work it out, you get this thing is b to the 2n squared plus 2, c to the n plus j, right? But you say, but 2 of this is not is equal to 2, 2 of these things squared, because this guy j is at least 1. And you say, oh, so because this is equal to 2 times n squared plus 1 plus 4nj plus 2j squared, and 4nj and this beats that. And you're thinking, okay. So it means that you accepted a string, hence M2 accepted a string which is not in L2. And you're thinking, you shouldn't have done that. So that contradicts the fact that L of M2 is equal to L2, hence L2 cannot be regular. So if you're not regular or non-regular. The point is number 6b takes a little doing to understand. So I will say do your best shot for number 1 to number 6a, and then, write something for number 6. Not everybody can get number 6. But if you had studied it before and practiced it when we were doing chapter 4, you would get it. And I try to make it as easy as possible each time, but I'm running out of questions, right? Running out of expressions. So I might have to start repeating. But I think my time is almost up. If you have any question, this is a good time to ask. And good luck in your test number 2. And as I said, don't concentrate on just one question. There are 5 questions. So number 1 and 2 is very easy. Number 3 is not so bad.